Hey guys, welcome back. I need to add in just a little bit more content on moment of inertia, and this is the parallel axis theorem. It's really easy, and it allows us, if we know the moment of inertia of something, if we shift where the axis is, to find out what the new moment of inertia is. You're going to do a whole lab that we do this with various different things. I'm going to do it for you guys for a hula hoop and a meter stick, and you're going to do it for a ruler, a billiard ball, and a disc. And what this says is that the parallel axis moment of inertia is going to be our original moment of inertia plus the mass times the distance that we shifted squared. So if we look at what our parallel axis is, it's going to be this big one that it was moved from. This is the one we know, the dotted line. We know what this value is. Our D is there, and M would be, excuse me, a known amount or a measurable amount. You guys are going to measure it in the lab. All right, so find the new moment of inertia of a hula hoop if it's rotated about its end. So if we look at a hula hoop, we would say that all of the mass is concentrated on the outside. So that would have the moment of inertia of a hoop, which is mr squared, which I derived for you guys. So our new moment of inertia is going to be equal to this plus how much we shifted it. How much we shifted it is going to be equal to its radius. And so I'm going to have 0.095 kilograms times 0.76 squared plus 0.095 kilograms plus 0.76. So now my axis is up here. And in the lab, we're going to find out what the period is of this, because that's often what they'll ask you to do. And so the parallel axis theorem tells me that this is about 0.11 kilograms meters squared. And these notes are like, I think it's one page front and back, so it's not a very big part. All right, so find a moment of inertia of a solid disk if it's rotated about its edge. All right, so again, a disk, I know, has a moment of inertia of 1/2 mr squared. So the parallel axis theorem tells me that it's going to be equal to this original moment of inertia plus this md squared. So looking at our disk, this was our original axis. We're going to shift it up by 0.15 meters. So there's our new axis. And you guys will do this we'll do it in the lab. So if I put in values, I got 0.07 kilograms meters squared. What was it originally? I'm just curious. It was 0.022 was what it was. And it makes sense that it's going to be harder for you to rotate it because you put the axis where you're going to have more of the mass farther away, right? Find the moment of inertia about a rod. If it's end, if it's moment of inertia about the center, is ml squared over 12. So we know that if we do it about the middle, that's going to be the easiest way to rotate this rod because there's equal amount of mass on either side. I derived this for you guys with calculus, and we derived about the end with calculus as well. And I did derive it at a quarter length with calculus. Maybe, I can't remember what that AP problem was, if it was a quarter length or a third length. All right, so I am shifting it to the end, so that's going to be a shift of L over 2. So that's going to be half of it. So I'm going to start with my original, which is ml squared over 12 plus md squared. So d is going to be L over 2. So I have ml squared over 12 plus m L over 2 squared. And this shows up a lot like in multiple choice. They'll have you do it with the rod and have you switch it. And I should note there is a perpendicular axis theorem that is not, we're not responsible for. All right, so this is going to be ml squared over 4. So I have ml squared over 12 plus ml squared over 4. The common denominator is 12, so I'm going to have ml squared over 12 plus 3 ml squared over 12, which is going to give me 4 ml squared over 12, which is 1/3 ml squared, which is what we were told when we first learned this and what we derived with calculus. All right, what about if I go a quarter length? So now I'm shifting it from there to there. So I'm shifting it by a quarter. Again, my new moment of inertia is going to be my original moment of inertia plus how much I shift it. So now I'm shifting it by L over 4. And so this is going to be 1/12 ml squared plus m L over 4 squared. And so this is going to be 1/12 ml squared plus ml squared over 16. Our common denominator is going to be 48. This one seems familiar as a multiple choice at some point. So I'm going to have 4 over 48 ml squared plus 3 over 48 ml squared is going to be 7 over 48 ml squared. And there'd be no reason for us to have that memorized. But you can shift with whatever you have as long as you know what the moment of inertia is. So that makes it a valuable tool for the multiple choice. And it will be in the lab. We'll see that it'll work out pretty well.